There will be some background on fridges today, but very overview level. Okay. Hey, today we review a very large area in science and technology, which is all the experimental techniques related to the experiments that we will be discussing during this semester. So this is a really a vast area, and I decided to squeeze it all into one lecture. Therefore, for the most part, I will just be flashing pretty pictures and explaining just the basic principle. But you can certainly follow up on the techniques that you like to know more about on your own or discuss with me. I think this is a good way to do this, and we all get a crash course, and we are all sort of on the same page in that area. The backbone of the experimental process of quantum transport is very naturally subdivided in three areas. The first area is typically done by another group. So you find really good chemists, material scientists who provide extremely high quality crystals to you, and of the range of the materials that we discussed last time. Materials for quantum transport, semiconductors, carbon systems. Well, carbon systems you can often grow on your own in a little furnace in your lab. But certainly semiconductors with a very low level of defects, you want to delegate that to experts who really know how to do this and who study the growth mechanisms. And then the second step, nanofabrication, the creation of nanoscale devices. You also really want to delegate it to somebody else, but normally no one wants to do this for you, so you do it yourself. And we will review how to start with a bulk material like a 2D electron gas and structure it into a nanowire or any device you want, how to put contacts on things, etc., etc. And finally, of course, once you have a device, after the nanofabrication stage, you would like to measure it, and there are multiple tricks related to that. In particular, how do you reach the low temperatures required for doing many of the quantum transport measurements? So three important stages in the process. So if you are a graduate student in the quantum transport field, you are going through these stages. You know, in my group, people are somewhere in between these two stages. We're a very young group, so we're not quite at the end yet, but we will be there soon. The last lecture was dedicated to, in a large part, or certainly in the central part, to high-quality semiconductors. For example, semiconductors like gallium arsenide, which include a group 3 element, gallium, and a group 5 element, arsenic. There are other compounds in this family: indium arsenide, gallium antimonide, gallium phosphide. So there are all very important semiconductors. They're all different in their band gap, in their spin properties, in their maximum mobility that you can reach. So they're all useful for different purposes. Some are more useful for electronics, some are more useful for photonics, and virtually all of them are interesting for quantum phenomena. And if you want very high quality semiconductors, pretty much your only option is to grow them using MBE machines, the molecular beam epitaxy technology. It is all happening in a big vacuum chamber. Let me just for a moment flash you this slide. This is a typical MBE tool. These kind of steel chambers are used to create ultra-high vacuum in laboratory conditions. So inside these chambers, vacuum is very high, means there are very few atoms flying around. Around the perimeter of this chamber, you arrange certain things you need to produce a high quality single crystal or epitaxial sample. In the center of the chamber you have the holder for the substrate where you grow your semiconductor. This holder rotates and it can be heated. The temperature is very important during MBE. And in front of it you have arranged a set of sources. They're called effusion cells. They contain very pure elements that you want to deposit on the substrate. For example, gallium and so on. And then inside this chamber, vacuum is so high that pretty much if atoms fly out of these sources, they travel completely in straight lines. There are no scattering whatsoever inside this chamber. Straight lines. In a way, it's ballistic. It's ballistic transport of atoms, right? Not electrons, but atoms. And on this axis of the chamber, they have located a number of tools that allow them to monitor the quality of the film that they're growing. So, for example, here you have the RHEED read gun. We will discuss what that is. But it bounces electrons here and collects them here on a screen. And based on the diffraction pattern that electrons make, you make a judgment about the quality of the film that you're growing. You can even hook up a mass spectrometer. You can attach another chamber to this chamber and another chamber to grow a different material on top, or to in situ, so without leaving vacuum, perform studies on the film, like do a scanning tunneling experiment or something else. Sometimes these chambers spider out into mini cities that take the whole room and also the supporting equipment around them. So these are very sophisticated technology, molecular beam epitaxy. In the essence of this technique, as I already said, are these effusion cells. They just contain elements and then you heat them up, and then at the top there is an opening through which you form a laminar steady beam of atoms that fly out in straight lines and land on your sample. Some of these slides have a Dutch flavor. So maybe they require some translation, or perhaps we can switch to Dutch if that's what you prefer. But for example, this means doping, and this means arsenic, and this means open shutter, and this means warm heated block, and who can tell me what that means? Ah, great. Okay, so the rest of the lecture will be in Dutch. Okay, so here in this example, this is a classical example where this imaginary chamber is set up for the deposition of gallium arsenide. So like in gallium arsenide, aluminum gallium arsenide quantum wells, two-dimensional electron gases that we discussed in length last time, and we will come back to many times again. Gallium arsenic, aluminum for aluminum gallium arsenide, and these very important things, dopants. So if you want to hole dope or electron dope your structure, you can put in silicon or carbon. Yeah?
I'm just curious if the relative orientation of the beams matters. Like if you're growing gallium arsenide, do they have to be at a certain angle from each other?
I think there are different designs and different tricks that people use. Yeah, and also depending on how many things you want to squeeze into one chamber, you might compromise on certain aspects. And you can control the different rates at which materials are formed by temperatures. So you have a powerful knob in temperature. Temperature plays an essential role, and temperature at every instance in the process. So of course the temperature of the effusion cells plays a role. You can see here that these group 5 semiconductors or elements, they evaporate at much lower temperature than these group 3 materials. So you have to adjust the temperatures of different diffusion cells differently. But also, when all these atoms land on your substrate, right? So when they all come here, they don't just stick. Well, depending on the temperature, they can also have certain mobility around the substrate. So an atom will land and then it will start traveling around. And so the temperature at this stage is extremely important, an extremely important parameter. And this is also, all of this is only to a degree a pure science, and to another degree all of this is art or magic, or maybe black magic. No, the urban legend is that a certain group, the quality of a semiconductor has degraded, and so they put a pizza inside, or someone left a piece of pizza in the machine, and then it went back to a million mobility semiconductors. So not everything is controlled in these processes, and sometimes it is required to train the chamber. You grow a recipe, and a recipe means turn this one on, turn this one off, and grow a certain stack of semiconductors, and you can grow the same recipe over and over again, and only after 6 months or 1 year will the quality reach very high levels, like mobility of 1 million or several million. And before that, who knows? So what happens on the walls of the chamber also has an effect. So many things have an effect. So this is a real art, and if you have a friend who does MBE, be very nice to him if you want to get good materials from them. Take them out for a lobster dinner or something like that. Okay, so MBE is the queen of growth, and this is how they can tell what is happening on the substrate in real time. So they do reflection high energy electron diffraction. I already showed where it might be positioned in the chamber. Here, once again, from a different angle, this is the substrate where we grow a semiconductor, and the beams of atoms coming ballistically down. But here we're sending these electrons sort of orthogonal, and this is just a fluorescent screen where you can see the diffraction pattern from these electrons. So for example, if you're growing a 2D perfect crystal, you will have a bunch of dots here, and if the dots are very small, means the crystal is single crystalline quality. If you're growing other dimensional structures, there could be lines on this screen, etc., etc. And if you monitoring one location on the screen, then the intensity at that location might be doing these oscillations. And by counting these oscillations, you can count single layers of semiconductor growing on the surface of the chip. So roughly, this is how it works. It's all about being sensitive to roughness. And okay, of course, how well you're focused, but the main idea is roughness. So if there is a lot of roughness, then you get a certain destructive interference. So here again, nieuwe laag, new layer, kwart laag, quarter layer, halve laag. Yeah, great. Driekwart. 3/4. Yeah. So they start with a perfect finished layer, and then you start growing the next layer, and they start getting these little clusters of atoms as they diffuse around the surface, and the intensity of the read signal goes down, and then finally when they reach the next perfect layer, the intensity is back up. So you go from destructive to constructive interference back and forth, and so they can just count as they grow. So they know what's going on in situ. This is very powerful, that they can monitor this monolayer by monolayer growth. And this is what they can produce. I told you that the recipes can be very different. So for example, here they changing from gallium arsenide to aluminum gallium arsenide many, many times. And these are all perfect single layers of one material after the other. So you might want to grow such a structure, I don't know what for, but maybe these are some kind of mirrors for reflecting a laser beam back and forth. Yeah? So some kind of an optical device. In a heterostructure that's used for quantum transport, you normally don't find so many layers unless you're growing some kind of a super lattice to relax strain or something like that.
In Reed, how do they account for the fact that the layers probably aren't going to grow evenly?
They do grow evenly.
They do grow
evenly. First they cluster, and then finally they form a perfect layer.
Okay.
And that is the art of MBE. So that is the epitaxy in MBE, growing layer by layer. So they tweak the growth parameters such that that is true.
Okay.
And they study the dynamics of how atoms diffuse on the surfaces versus the influx of atoms. They have various models for that, and
so you don't get little clusters where there are like 2 layers and then 0 layer and then 1 layer.
Okay, so actually I stand corrected. You can have also little pyramids growing, for example. So another thing that plays a role is the lattice mismatch between the substrate and whatever you're trying to grow. Yeah. So in the case of these two materials, the lattices of these two are very well matched. So they can produce these perfect layers. And if you put something that is very mismatched on top of gallium arsenide, like indium arsenide, it will form little pyramids rather than layers growth. So you can grow a number of things. Yeah, I did not cover the self-assembled growth in this lecture, but we will also see how you can grow nanowires, for example. That's very different, a very different method. I think it's actually coming up. Yeah, so this now we're talking about a different technique, not MBE, but MOVPE or MOCVD. Metal organic vapor phase epitaxy or metal organic chemical vapor deposition. They are very similar techniques, although epitaxy again stands for single crystalline quality with a layer by layer control over the growth. But in contrast to MBE, this happens not in ultra-high vacuum, where atoms fly ballistically in straight lines. This happens in the presence of a bunch of different gases. It happens in a tube, which is the reactor, and here you put your growth substrate, and then you have to flow various precursors which decompose into the desired semiconductor when they hit the substrate. You have to heat the substrate, and this is also a very powerful technique, especially due to a huge range of semiconductors you can grow in a single reactor. So here again, temperature plays a crucial role. At very high temperatures, atoms have so much energy as they hit the substrate that they diffuse all over the place. And so you tend to grow layers, epitaxial layers, two-dimensional layers. And when you lower the temperature, then you can induce the so-called catalytic growth, where semiconductor is nucleated only at the places where you defined it by depositing catalysts. We will come to that later. And the precursors that you might want to flow through this reactor are listed here. Some of them are these organics, for example, trimethyllindium. It has an indium atom attached to a bunch of organics. And so when this gas hits the substrate, all that organics is disappearing and the indium atom is left. And then for group 5 you have these elemental gases, and these are actually extremely poisonous. So phosphine and arsine, a small amount can wipe out a city. So there's a lot of safety associated with these MOVP reactors. Sometimes all the security costs more than the reactor itself. This is how the reactor looks. This is quite a bit different than the MBE chamber, right, with all that steel. That's because vacuum is not high at all here. Here you're actually trying to prevent the dangerous gases to escape from the reactor, not prevent air to leak into the reactor. So there are all these pipes for rapid evacuation of if there's a leak. And you can't even directly handle the chips. You have to go through these rubber gloves, stick your hands in these rubber gloves and go inside. And in the back of the reactor, you have this manifold of lines that run to various chemicals, various precursors. So you can hook up really a huge range of precursors to produce pretty much the entire range of semiconductors in one reactor. So that is nice.
Is this more suited for industrial applications than MBE?
Both are used for industrial application, but certainly this one, so this company, I think it's called Edison, installs hundreds of these reactors in Korea and where they grow things, like for screens and stuff like that. And but MBE machines are also used. So I think all the chips are made by MBE, if I'm not wrong, if I'm not mistaken. I think both find industrial applications heavily. Okay, and here you can see the photo of one of the reactors. There are all kinds of different models, but this is the tube where all these gases combine. And the nanowires that my group works with are produced using MOVPE, and it is also a very interesting and fascinating process how they grow, and quite a bit different from MBE. The biggest difference comes from the fact that you have this gold particle which catalyzes the growth. You can see in this diagram that this nanowire semiconductor only grows underneath the gold particle. So the way it happens is, and we are not in high vacuum, we have all these precursors flying around, and at a certain temperature where this process is favored, when the precursors like trimethyl indium and arsine hit the surface of the catalyst, they decompose. So they throw away all the organics, all the hydrogens and carbons, and then they go into the gold. And then it becomes a gold alloy, for example, gold indium alloy. And then that alloy keeps absorbing indium until it reaches a certain supersaturation point, after which indium precipitates underneath the nanowire, combined with arsenic. So indium arsenic precipitates underneath and pushes the gold particle up, and so the gold particle moves up, leaving behind this nanowire. And these can be also single crystalline. But that's not the only thing that's going on in the same reactor. You have other sort of processes happening at the same time. Rather than going into gold and decomposing and precipitating, the same atoms can also hit the substrate and either grow a two-dimensional film, which is bad, or they can travel and diffuse up the surface. So there's different competing mechanisms. Another thing that can happen is radial growth. So you have this nanowire, and these atoms of indium and arsenic stick to it from the sides and making it fat. So sometimes the nanowire looks like a cone. That's because this part was around longer and it grows this way farther than the upper part. So there is some certain tapering to the nanowire. So you can also produce heterostructures with this method. For example, go from trimethyl indium to trimetal gallium. That was not so creative. And then you start growing gallium arsenide, and you can do that without changing the wire. So you will have a section of indium arsenide, a section of gallium arsenide. So just like in 2D MBE growth, you can produce heterostructures. And these one-dimensional sort of nanowire structures also have an interesting advantage over bulk growth related to defects. You see, in the bulk, when you grow 2D films, it's much easier to create defects. That's because, for example, if you want to grow one semiconductor on top of the other, and they are a bit mismatched, this is now an infinite surface from the point of view of single atoms. And so the strain that you build into this structure has nowhere to go. It stays in, and then it produces various defects. For example, here, to maintain this lattice above, the system decided to skip one bond. So this is a defect. And these kind of defects, remember, in the case of two-dimensional electron gases, at the interface, right here is where the gas will be formed, ultimately. So these defects sit right there. So this is a very bad defect for the purpose of quantum transport. And now imagine if this is your entire layer, then going from one semiconductor to the other, you can just expand a little bit the positions of atoms on the side close to the surface, because the surface to volume ratio is so high. Then strain is easily relaxed when you approach the surface. So this is a difference which allows, by using MOVPE, to combine a much larger range of semiconductors in epitaxial process. So without forming these self-assembled pyramids, but forming perfect layers inside a nanowire. Now here's another technique. I think this is how materials are produced in Levy Group. They collaborate with an excellent group in Wisconsin. This technique always fascinates me, because what they do is they take a vacuum chamber, right? Recognize this from the MBE slides. This steel thing is a vacuum chamber, but it has a window, and then they stick a huge laser next to it, and then through the window they shoot the laser at a certain target, whatever you want to ablate, and atoms just get blasted out of this target, and they hit the substrate. Amazingly, you can produce extremely high quality, extremely complicated compounds. So now we're not talking semiconductors. For that we have MBE, MOVPE, but we're talking really complicated stuff, like all these pnictides, high temperature superconductors that have crazy formulas. If you add doping to this is yttrium, barium, copper oxide. This is bismuth, strontium, copper oxide, I think. Or these lanthanum, aluminum oxide, strontium, titanium oxide materials can all be produced with very high quality using this laser ablation method. So this is another method.
How does it compare to MBE?
Well, I think in these complicated crystals, there are many internal degrees of freedom where atoms can move slightly, or the crystal cells can even turn positions a bit, and there's not much you can do about it. They are also not stoichiometric. Often you want to dope them with oxygen, and so the amount of oxygen varies per cell. And so I think even if you were able to tune up epitaxy for these films, and some people do, there are groups that I think also do epitaxy. Still, the film quality is not exceptionally better. Better with epitaxy, but not orders of magnitude better. So I think there is a certain advantage to just having a target and blasting it. It's much easier. But you can do MBE also. Is that the question?
Yeah, I just curious why, like, people in oxide use a PLD but not like MBE.
Yeah, I think it's convenience also.
The best quality oxides are probably grown by MBE.
Yeah.
Yeah, so you can do better quality, but it will be required to do that. Okay, so this summarizes the growth part. Took a bit longer than I thought. And now we're going to the second module, the nanofabrication. And here there are several important concepts. So what we want to do is create from a bulk, a semiconductor, for example, or another material, a narrow path. We want to pattern it into a structure. It could be a semiconductor, a metal, an oxide, but the technique is the same. It's called lithography, and we will review methods of lithography in a moment. And then quite often we want to take the created pattern and either metallize it or etch it. So do something to the substrate, but only where we defined the pattern. And those are the techniques listed here. So we can evaporate a metal, or we can etch using wet or dry chemistry, or mechanically. So many of the lithography techniques rely on shining a beam of electrons or photons or ions on your substrate, and oftentimes changing locally the property of an additional chemical you put on, which could be a polymer called resist. So this resist, in the case of electron beam lithography, will be sensitive to electron beams, and where we shine the beam, we will later be able to remove that resist in a solvent or otherwise. And thin film evaporation is a technique somewhat similar to MBE, except it is not done in ultra high vacuum. Again, you have a boat, a little boat with metal, and you heat it with electrons, or you can just heat it with a heater until these atoms melt, and then they form a vapor that goes on your substrate. The requirements for high vacuum are not so high because we don't care about epitaxial growth, yeah, single crystal layer by layer growth. But it requires high vacuum. So for example, you can imagine exposing a straight line here, then removing the resist in a solvent, and then evaporating a metal, and the metal will stick to the substrate only where you wrote a straight line. This is how you do lithography, patterning. This is just to summarize for you that there are different kinds of vacuum, and different people also have different definitions for what is considered low vacuum, high vacuum, and ultra high vacuum. I pulled this off the internet, but I think MBE people would want to, for example, move this line further down here. For them, ultra high vacuum begins at maybe 10 to the minus 10 torr. And if you're curious, you can also see the mean free paths that you can reach. So the MBE machines operate down here, and that means that the mean free paths you can reach are truly gigantic. Okay, I already described in a few words what lithography is. Here's what lithography can do. Yeah, you can envision in your design program a multi-layer structure. Yeah, we're doing this tomorrow, right? Yeah. And then, yeah, you can implement it pretty much how you designed it, but you have to do many steps for that. This is a chip for producing metric screws. So you can have to do many steps. For example, this is, I took this from my thesis because I already had the slide and I was lazy to make a new slide. But here is starting from a silicon substrate, a couple different ways how to make a niobium ferromagnet niobium junction. So you can make a niobium layer which is flat, then deposit a patterned layer of ferromagnet, then you want to make a window of dielectric, and then on top of that layer you want to put another superconductor niobium, and then in this area you can observe transport from the top niobium to the bottom niobium. Or you can go the other route, grow a tri-layer of niobium, ferromagnet, niobium, and then etch it down here, etch it down here, backfill with an insulator, and then deposit another layer of niobium on top. So here are two different routes of reaching the same thing.
And how do you choose?
Well, this was a smarter route because here all of these three elements are deposited in one vacuum cycle, and so the interfaces between them are supposed to be very clean, because every time you take the thing out of the machine, expose it to air, you can contaminate. So you can see here the first layer is produced, and a second layer after lithography, a third layer, etc. So this might have disadvantages, but in the end these were the samples that gave interesting physics. So how do you choose? Choose what works. Okay, so in photolithography is the most basic lithography. Again, you can have a substrate coated with an organic compound, polymer, which is called a photoresist, and then on top of that you press a mask. This is a glass plate with some structures already predefined on it, and then you shine light through this mask, and this works like photography, because the areas that are open get exposed by light, changes locally the properties of this photoresist, and after that I can wash it off in a developer. Like you develop photographs, you can develop this pattern the same way, and then I can be left with these kind of patterns in the case of the negative resist, or these patterns in the case of the positive resist. You can see these are complementary, and then I can do whatever I want with it. For example, in this case I remove this oxide, so I etch using some etchant, and I am left with this kind of pattern. That's the principle. You can do this, this is the state of the art in this technology. If you don't use just light from a light bulb, but if you use lasers and certain focusing lenses, you can go down to very small resolution with this technique, because typically you would think this gives you wavelength resolution because you're using light, but you can go way sub wavelength, and I believe this is how Intel chips are printed, using optical lithography, but in very fancy machines like those made by this company ASML in Holland. But we don't need this, because this is really industrial scale, working with many big wafers. This is another powerful method that is maybe something like 10 years old. You can have literally a rubber stamp, but with very tiny patterns on it. These could be some nanometers, so resolution can be 22 nanometers, and you take this stamp and you press it down on your substrate, and you can stamp in the pattern that you like in a few different ways. There is a PDMS stamp, nano imprint lithography, or this kind of thing, but in the end it's the same thing. For example, in this case you just squeeze out a certain compound out of this by pressing a stiff stamp down, and you end up with this pattern, and you can by etching define a pattern like this. So again, this is very nice. You need to have this imprint ready, and it's very hard to change the design of it. And so this tool, electron beam lithography, is maybe the most flexible one for research applications, but it's one of the slowest ones. But here, basically, by using now electron beam resist, but in analogy to photoresist, you can expose electron beam resist with a beam of electrons, but you can control the beam of electrons, how it moves, using the standard scanning electron microscope technology. What scanning electron microscopes do is they just raster the beam of electrons to give you a picture. Now they raster it like your TV, continuously in a grid. But if you were to take that beam and take control over it, you can draw any pattern you like with it. So if you add a pattern generator to your SEM, you can turn a scanning electron microscope into a beam writer. And people do that. People take a $5,000 old SEM and buy a DAC card and turn it into a beam writer. Of course, that doesn't work very well. If you want good results, you want to buy a very expensive machine. This machine, I think, is from Leica, if I'm not mistaken. And this one would cost $5 or $10 million. The one we have at Pitt is from Wraith, and that one costs about $1 million. And you can write anything you like with this technique. Again, the way it works is by exposing electron beam resist. And the power of this technique is that if you want to write a bunch of electrodes that come down to this particular area on your chip, and this area is every time in a different place for every experiment, this is the way to go. And what is very important in electron beam lithography is that a lot of the exposure happens due to backscattered electrons. These are the models of how electrons travel inside the substrate as they hit the surface. So this is the point where we focused the electron beam, and so they're all concentrated here, but they continue their trajectories and they scatter back, and oftentimes they fly back. So this so-called pear-shaped plume is a very important concept in electron beam lithography, and by knowledge about that plume, you can improve the quality of your e-beam lithography. And this plume can extend quite far away from the surface, many microns.
So this is a picture of the path of the electrons, right?
I think this is a simulation. It's hard to take a direct picture, yeah. A numerical simulation.
Yeah, so could you give us a picture of the breaks of the PMMA form?
I could, but I don't have it now, so
okay,
I can
so
show you later.
Could you explain it roughly? Is it similar to these two pictures?
Well, so your question is about specifically how exposure by electron beam happens. And it happens by taking a very long molecule called PMMA, which is poly-MMA.
Yeah.
So this could be 1 million MMAs stuck together. So it's a super long molecule. And then you cut it with electrons like with a knife. Yeah? So the high energy electrons just shred this molecule, and when it becomes shorter, then it dissolves in solvents. So then that is how you expose. And so what I'm trying to say is that not only these initial electrons that fall down shred the molecules, but also the ones that come back from scattering. They also participate in that process.
Yes, I know. But compared to the path of one electron, right? We are more interested in the situation of the bounds of PMMA, right? After, for example, 10K or 20K, what's the difference?
Let's talk later about this.
Okay.
I'm trying to get a big overview. So, yeah. Okay, another method is focused ion beam. Instead of electrons, now we are using ions like gallium. We're forming a beam from them, and with these ions we don't have to even use a resist. These ions can directly mill through the material like that. So you can directly cut holes with a beam of ions, or you can even grow structures out of these ions. And the point of this slide is that the two techniques are in principle very similar. You can do almost one-to-one mapping between electron beam and ion beam. You just need to replace the E source, which is a cathode, for example, just a heated wire which emits electrons, with a certain source for ions. Recently, a new technology has been the helium ions. There is a helium ion microscope. You can also do writing with that. And that is a compromise between this devastating gallium beam and electron beam, which is very light. The helium ions are relatively light. Okay, here I would like to show you, guide you through the steps of a fabrication process, kind of a nano cooking that I myself did. I thought that would be fun. In this case, I used a surface of a gallium arsenide, aluminum gallium arsenide heterostructure, right? So the one that hosts two-dimensional electron gases, something like 100 nanometers below the surface. One thing that you could already deduce from all the things I said is that those materials are extremely precious. A research group might get a little piece like that, and they have to make it last perhaps for 5 years, if it's a really good material. So there is no room for error. You cannot make a mistake and throw that chip out and then call the grower and say, hey, the wafer is finished, send me some more. You might have to wait several years. And this sort of defines various pains I had to go through with this chip. So first of all, first you practice several times on just a gallium arsenide wafer without the two-dimensional electron gas. And then this is a computer model that represents a particular little piece, 5 by 5 millimeters, and I was hoping to squeeze about 30 different devices on that one chip. So they're all start from these blue square pads. I will explain what they are later. And the devices are these concentrations of yellow lines that come together. And so these are the electrodes that come together into a device. Now these little specks and these scratches is me mapping out all the little defects that I could see in the optical microscope on that chip. And my goal was to route all the lines and put devices in between these specks. Because I could not get another piece of this wafer, and so I had to live with all the defects. You know, MBE is a great technique, but if you zoom out a bit from the atomic scale, there could still be some defects on the micron scale. So this is how the chip looked after it was finished. Now yellow is gold, mostly gold, and there are certain regions etched, so these rougher regions are etched, and therefore these rectangular shapes are separated from one another. So in between there is no two-dimensional electron gas. And if you zoom into one of these devices, it is a structure like this. What you see here is gates. Remember gates? So these gates come together to form this narrow channel. The length of this channel is about 100 microns. This is why it was so painful to find areas without little specks where I could define these devices. And the width of this channel is 1 micron. So this is not technically nano, except in between these gates there are little gaps which are a couple hundred nanometers, and those are quantum point contacts. So that makes it technically a quantum transport experiment. In between the gates there are ohmic contacts to inject electrons into the two-dimensional electron gas. If we zoom in further, now we can see the little gaps. So these will be the quantum point contacts about 20 microns apart, 10 microns apart. And by the way, this is a pattern in PMMA. This is an inside comment for my group. And then how do we go from the world of chips, which are 5 millimeters or so, to the world of electrical wires, which we can pick up with our hands and plug into the amplifiers? Well, we have to do some little wires in between. These are called wire bonds. They are like little gold wires that connect sort of bigger pads, millimeter scale, to these tiny pads on chips. This image is from Levy Group. When we were testing our wire bonder for the first time. And the machine, the wire bonder machine that makes these little gold lines is like a sewing machine. It comes into the needle and goes pick, pick. So when you operate this machine, you are looking in the microscope and you are making these bonds. And so these bonds provide a connection between the nano world and behind this chip carrier, the macro world of electrical wires. And that transitions us into the last stage of the process, which is once you've made the full chip, you went through 5-10 different steps of fabrication, and you made the wire bonds at the end. You want to measure it. And as we are in a quantum transport course, then the measurement is always roughly the same. It's a measurement of voltage or current going through the device. But there is a lot of technology surrounding this measurement. Specifically, I want to focus on how to cool things down. And there is a range of different techniques, but pretty much most of them involve cryogenic liquids. So if you dunk your chip in a bucket of liquid air, which is nitrogen, you will get to about 77 degrees Kelvin. Which is about minus 200 degrees Celsius, and God knows how many Fahrenheit. But let's say 77 degrees Kelvin. And if you remember my introductory lectures, 77 degrees Kelvin is kind of on the edge. It's a bit too high for quantum transport. Now the KBT, the thermal energy, is larger than most of our quantum energy scales. The Coulomb energy, the orbital energy, those are all something like millivolts. And 1 Kelvin is 100 microvolts. So 77 Kelvin is towards 10 millivolts. So that's a bit high. And so you want to use a cryogenic liquid, which is helium. And helium liquefies at 4.2 degrees Kelvin. So if you have a bucket of liquid helium, like one of these, this or this, then you can be sure that you are at 4.2 Kelvin. So oftentimes the way these experiments are done, you might have your cryostat, and of course this liquid is immediately evaporating if you put it in a regular flask or like in your coffee cup. You have to have an isolated cup, which is called a dewar. So it has layers of vacuum and isolation. Pretty much what works best, the modern technology says, is layers of this plastic called mylar coated by aluminum. So that is called, the fancy word, super insulation. But it is very simple. But a bunch of layers, like when you go snowboarding, you want to put a bunch of layers on. So you put a bunch of layers of this mylar and you become super insulated. Then you can keep your helium liquid and not evaporating for many days. So you have time to do your experiment. And if you run out, you can always take a transfer dewar and transfer more helium by squeezing on this balloon and creating overpressure on top. So this is a very conventional way of doing this. It works. And the good news is that you can even go lower than 4 degrees Kelvin by pumping on this helium. So if you create a lower pressure above this helium, you can reduce the temperature. This is basic thermodynamics. PV equal RT. You pump on a liquid, you extract the more energetic atoms, and the temperature drops. So then great, why don't we go to a nano Kelvin? Well, because the lower you cool, the lower is the vapor pressure of helium. So when you reduce the temperature of this helium bath to something like below or around 1 Kelvin, the vapor pressure above here becomes so low that it is impossible to extract any more atoms with any reasonable pump. So pretty much with this liquid, helium-4, you are limited to stay above 1 degree Kelvin. And there are many wonderful experiments that you would like to do below 1 degree Kelvin. Yeah? So this graph shows you what happens. Notice that on this axis it's a linear scale where you just have a range of a few degrees Kelvin, but on this axis it's a logarithmic scale. And the pressure drops dramatically, very fast, as you lower the temperature by not so much. And who knows what happens here? Into what? Superfluidity. Yeah. Okay, so if you want to go below 1 degree Kelvin, all you have to do is switch an isotope. You go from helium-4 to helium-3. Doing that, you can reach somewhat lower temperature. You can reach actually temperature of about 250 millikelvin. So you can improve by a factor of 5 or 6, realistically, over helium-4. That comes at a high price. Helium-4 is pretty abundant. It is often found with natural gas deposits. So you just have to collect it from the top of natural gas because it's a lighter gas. But helium-3 is only produced in atomic weapons programs, and which were all shut down, and it has a certain half-life. So it's a very precious element, and that's why we don't want to let it out. We don't want to just blow it in the air, and we always keep it in a closed cycle. So if you want to run a helium-3 cryostat, you create this confined contour in which helium-3 lives, and you have to do it in a sequence of steps. So when you start, all your helium-3 is in the gas phase in this vessel. Then what you do is you want to condense it into liquid. The way you do this is you exchange, you put in contact with this helium-3 space helium-4 on which you pump, and so you reach a degree Kelvin temperature here. So you reach 1 Kelvin in this one spot, and when atoms of helium-3 fly around, they decide, oh, it's so cold, I will drop down and become a liquid. So once you've condensed all the helium-3, then you actually heat up a section here which has charcoal, just charcoal. And the charcoal, you stop heating it. Basically you use this absorbing properties of charcoal to use it as a pump. But this pump lives inside this closed space. So there is a piece of charcoal here. As soon as you stop heating it, it starts pumping on this gas. Right? Charcoal has a huge surface area, so atoms stick to it very nicely. And so it is like a pump. It is called a sorption pump. And so by that you can reduce the vapor pressure of helium above the liquid, and by the same principle you cool down and you reach lower temperature. But that temperature is still not quite low enough. You may want to go even lower. And that's when you have to go for something much more advanced than these simple pour something and pump it out cryostats. One example is this dilution refrigerator. Dilution means that it operates on a mixture of helium-3 and helium-4. And what produces cooling is the process of dilution of helium-3 in helium-4. And by the way, the reason why we always come back to heliums, helium-3 and helium-4, is that those are the only two quantum liquids, so liquids that theoretically remain cold all the way down to 0 Kelvin. So unless you apply pressure. This is due to certain quantum fluctuations. They remain liquid. And of course, for most refrigerators, like a fridge in your kitchen, you want to run some liquid in a loop and do some thermodynamic cycle of heat exchange. And therefore, you want something that remains liquid down to very... So the machine, the helium, the dilution refrigerator is very complex. This is a cross-section of one of such machines. It has multiple stages of different temperature. 1 Kelvin, this is a few hundred millikelvin, 50 millikelvin, and finally this mixing chamber reaching into maybe 5, 7, 10 millikelvin. So first let me go over the principle and then a little bit about technology. Maybe I can even answer one question, if I can. The principle is also evaporative cooling, but it's pretty advanced. Basically, the way you start running this machine is that you condense this entire mixture into the bottom of the fridge. Again, using a 1K circuit with helium-4, conventional helium, which is another circuit, external, you make all of this helium-3, helium-4 liquid down here. And then when it's cooled below a certain temperature, which I don't remember, but it is in between 1 and 3 Kelvin, this mixture phase separates, and all the helium-3 floats above helium-4. It is lighter, it floats above. Technically, this is called helium-3 rich phase, and this is called helium-3 poor phase. But for the purposes of this lecture, let's just call this helium-3 and this is helium-4, even though they're actually intermixed. And then, once this happens, you hook up a very big pump here and you start pumping. And what actually tends to happen is that what you're pumping around this loop and then feeding it back here is just helium-3. From this phase boundary, helium-3 evaporates down. This is very counterintuitive, right? Normally you think things evaporate up. Steam evaporates from the pot up. This one evaporates down into helium-4, and then it gets sucked out, and then it gets put back in. And running this helium-3 continuously around the loop, that's what gets you to millikelvins. So it has a lot of cooling power and sustains to very low temperatures. But of course, to convert this principle, which, you know, maybe 50 years ago people were studying this fundamentally, this phase separation and this process. This was a subject of science. I have a thesis in my office from Delft from the 1970s. The title is Some Measurements in Liquid Helium-4. You know, at that time that was enough to, you know, do some measurements in helium-4 and you can get a PhD. Not anymore. So you just treat this as a machine. Then you do not just some measurements, but very particular measurements. But someone had to work out how to make this practical machine. And what tends to be very crucial in this technology is, so in between here, the gas goes to room temperature where there is a big pump, and so then it's at 300 Kelvin. And so what tends to be crucial is how to cool back down this gas, and that is what these arrows are showing. So in the actual machine, the path out, which is a big line, and the path down are intertwined in these loops, which are called heat exchangers. So the gas that goes up cools the gas that goes down. And when people figured out that they can do that, they started reaching millikelvin temperatures in working devices. And then a lot of detail goes into the design inside this mixing chamber, because it is yet an extra challenge to take the cold, which is in helium, which is in the mixture, and transfer it into the metal, which is outside. and where your sample might sit. So inside the mixing chamber you have these complicated fan structure, and the coating of this fan structure is also a separate art for which you can write many different dissertations. Okay. So one question, or we were discussing fridges, so okay, you will read the book. And then actually it's a wonderful mature technology. It is still fringing on art, but it is quite robust. We are getting 4 dilution fridges at Pitt in the next few months, 2 in my group and 2 in Levy group. There is one here already. You can come and see it. It's a beautiful machine, but there's always a but. Recently we encountered as a community a very strange problem. This helium-3 became unavailable. So basically the US government sequestered all of it because it is used in radiation detectors, and they want to make sure that they have it if they need to radiation detect a bunch of trucks coming from Mexico or Canada, or ships coming from abroad. So actually someone told me that most often these detectors are triggered by cat litter coming from Mexico, because that's slightly radioactive. So that's where helium-3 is used for real. But there is low temperature research and quantum transport. There is medical research and some nuclear research which relies on this gas. And like I said, we already do a very good job of keeping it. We run it in closed loops, and we're paranoid about not losing it. So for example, this person is a very prominent quantum transport physicist, Moti Heiblum from Israel, and he has many prominent publications in Nature and Science, in all kinds of journals. And this one is in Science, and so he made it into Science, but they put his picture in Science in this instance because in their lab they lost some helium-3. So they lost it, and they could not run their system. So that got him into Science. So you don't want to go to Science for that reason. So this is a big problem that we are facing, and we might be forced to switch to even newer technology, or actually it's been around for a while, but it's maturing now, where we don't need any helium-3 or helium-4. And that is called adiabatic demagnetization. That is pretty neat. Basically, you run a thermodynamic cycle, but with a solid material. You don't have this liquid going around in a loop. You use a solid. And the way you're extracting heat from it is by playing with the entropy of this material. The diagram is shown here. This material, it could be some magnetic alloy or certain salts which have magnetic properties, has spins in it, and you start at the base temperature, at the high temperature, and then by slowly applying magnetic field you order all the spins. Okay, then you have to subtract the heat, because the entropy dropped, the heat increased, so you have to exchange it with something else to get rid of that extra heat. So there are certain preparatory phases, but then at the end of the day you're left with a system of ordered spins at the same temperature that you were at. And then you gradually remove this magnetic field, and the spins start to fluctuate and disorder. And because the entropy increases, temperature goes down. This is a somewhat closed system, so that's what happens. And then for a while the temperature remains low. It's lower by delta T, and after a while, of course, you get some heat leaking into the system, and the temperature goes back up to that value, and you can repeat the cycle. There is a direct analogy between this process and the more conventional thermodynamic process, where you put your thing you want to cool in contact with colder and hotter elements. And not only you can get rid of helium-3 in this, way. But you can also go to much lower temperatures. You can reach temperatures of single millikelvins, and in certain instances microkelvins. And when you go to such low temperatures, you see new physics. For example, you can see the superfluidity of the goddamn helium-3. It's a fermion, so that happens at a much lower temperature. Or perhaps you can observe all the nuclear spins in the material, which normally don't care about temperature, suddenly orienting and forming a ferromagnet.
Can you find magnetic fields to your sample?
Yes, this is done by proper design. So here is, by the way, a working system that I've seen a month ago at UCSB. I took this picture, and yes, you can have a magnetic field. You just need to separate this magnet that does the thermodynamic cycling from the magnet that you are using a sample for. So I think in this setup, the sample is down here, and this is Pedrama. He did actually his undergrad at Pitt, now doing a postdoc at UCSB. So he worked with Sheldon, yeah. So he's hooking up this system. Yeah, so he will have a little magnet here, but the magnet that cools the fridges, I think, up here, if I'm correct. And the efficiency of these machines is judged by how many kelvins you can get per Tesla. So with these gadolinium substances, you have to go to a pretty high field. For example, if you want to cool from 4 Kelvin, the helium temperature, down, you have to go to few Tesla. But with these paramagnetic salts, even fields below 1 Tesla, which are fairly easy to make, can cool you down very efficiently. So there is a whole research going on about these compounds. Okay, I have 3 minutes left, so let me be a little bit quick. This slide makes a very important point, maybe the most directly related to quantum transport. And it is that, okay, now I've explained to you that we can make this nanostructure with the help of growers and in the clean room with nanofabrication techniques, and we can cool this chip down to the desired temperature. But not so fast. What we cool down in this process is the lattice. We cool down the phonons and the atoms of the semiconductor and of the metal that we made. And we did not cool down the electrons. So this is a very important thought. The electron temperature is not the same thing as the lattice temperature, and as a consequence, as a temperature of your fridge. These are 2 different temperatures. And that's kind of easy to see that, because we connect wires to the sample, and these wires go to room temperature, where electrons are at 300 Kelvin. Yeah? And then, if you imagine a thick copper wire going down, electrons flying very fast down to the low temperature, to helium, kelvins, so temperature drops by 300 degrees. But if electrons are not interacting much with the lattice, they're not exchanging heat with that lattice, their temperature can be very different. So the way to think about their temperature is to draw down their distribution in energy and fit it to a Fermi function and see how broad is that function. Is it as narrow as it needs to be for millikelvins, or is it very broad? So in that sense, the concept of heat and the concept of electrical noise become the same, because what electrical noise that is inherent to all electronic circuits does, it broadens the distribution of electrons in energy, kicks them around, and so it can be viewed as adding heat, temperature to the electron system. And for that reason, if we have a dilution refrigerator going from room temperature to about 1 Kelvin to base temperature of millikelvins, we have to make a bunch of precautions where we make sure that the electrons have a chance to cool down to the lattice temperature. And the simplest way to do that is to let them spend more time at each stage. For example, by wrapping the wire many times around some post at 1 Kelvin, I will give electrons more time to interact with the lattice to release the heat, to cool down electrons through things like electron-phonon interaction. And so the simplest thing is to wrap it down. Or more elegantly, I can put just a simple resistor in a circuit. When I put a resistor in a circuit, I slow down electrons, right? Because I'm introducing a drift velocity for these electrons, which is much slower than their Fermi velocity. So by placing resistors down, I can cool electrons down. And more explicitly, if I want to fight specific frequencies in the noise and interference that comes from the outside of the fridge, for example, 60 hertz is a very common thing, right? It's in all the plugs in this room, there's 60 hertz. My cell phone makes a certain noise, which is at gigahertz frequencies. The lights that are flickering, the fluorescent lights, that's kilohertz. There are all kinds of, if you read the full list, you can develop a real paranoia for all these noises. And you don't want your device to see any of that. And so then you engineer a sequence of filters that cover various bands in the interference and in noise that you care about. So for example, you can create an RC filter which will roll off at some kilohertz, or more advanced filters like pi filters or copper powder filters that cover other ranges. So this is the transmission of a filter as a function of frequency. And the statement I want to make to end this lecture is that if you want a good signal from your nanoscale device, you want to cool your electrons down and filter out the noises and interferences in this entire range. And therefore, you will create several stages of filters in your fridge. So, thank you very much.